Today's session, the talk is by Dr. Nitin Singh, and he will be speaking on verifiable decentralized AI pipelines using zero knowledge proofs. Dr. Nitin Singh is a researcher at IBM Research India, working in the area of applied cryptography with focus on privacy preserving machine learning and decentralized identity, employing cryptographic techniques such as zero knowledge proofs and multiparty computation. He completed his Bachelors and Masters in Computer Science from IIT Delhi and later obtained a PhD in Mathematical Sciences from IISc in 2014. In between, he has worked as a software engineer at VMware and Veritas. Before we move on to the talk, we would like to request the audience to subscribe to our Google group for information on future talks. You can also visit our website for more details. I'll be pasting the links in the chat box. Please do check. Finally, we request the audience to keep your microphones on silent for the duration of the talk, except when asking questions. And for questions, you may unmute yourself and ask Dr. Singh directly or type them in the chat box and we'll relay your questions. Over to you, Dr. Singh.
Thank you. Thank you for the nice introduction. And I'm happy to be talking here. Normally, I would have come to IISc, but due to non-stop rains over the non-stop rains, I could make the trip there, but hopefully we'll get there sometime else. So today's talk is on verifiable decentralized AI pipelines using zero knowledge proofs. This is based on joint work with my colleagues Pankaj and Vinayaka, and is to appear at Financial Cryptography 2022. Since I do not assume that a lot of audience here is like very intimate with the cryptography, I'll try to keep this talk at a more accessible level. So we'll not go into the details of the techniques and stuff. Mostly what we'll talk about what is the problem that we are trying to address here, how it can be potentially useful, and I'll just sort of give a flavor of some of the techniques which might be interesting even for people who are not from core cryptography background. So with that, let's start. So we start by defining what is a decentralized AI pipeline, right? So like a typical AI pipeline, when we consider it involves data gathering, then curating data, and then training models on data, and finally end users who will use the model to get predictions, right? Now, by decentralized, we consider when these operations may be executed by different organizations, not by the same person. So there might be organizations that specialize in collecting high quality data. So, and then there can be next set of organizations who curate data from various sources and produce data sets for specialized tasks or specialized analysis. Finally, there might be organizations which consume these curated data sets to, one is to build their models, train their models, and also to benchmark their models. And at the end of the chain, there are model consumers who essentially use these deployed models to get some predictions. So this is roughly the partitioning as we'll see in the figure here. Yeah. Yes. So this is roughly the 4 split that I described in the earlier slide. So on the extreme left, we have data owners who are, in some sense, they are trusted sources of high quality data, right? So for example, for medical domain, these might be hospitals who have clinical trial data, or for financial domain, these might be banks which process loans and stuff. So you may have like loan data, data on loan approvals, being granted, loans being granted. Right? Then next to data owners, they're data curators. So what data curators typically do, that they will lease data from data owners, or they'll buy data, purchase data. So data owners are going to obviously want to monetize their data. I mean, to compensate for the effort they probably put in to gather it in the first place, right? So data curators, they may collate data from various data owners, and they sort of produce data sets by performing some operations, let's say collection, filtering according to the particular use case, and producing specialized data sets, right, for different analysis. These curated data sets then are used by model owners to both train their models and benchmark the performance of their models, right? Model owners would want to benchmark their models on data which is curated from trusted data sources, right? Because that makes their sort of models more legitimate or representative of the real world, right? And finally, at the end of this pipeline, there are consumers. So these are end consumers like you and me. We supply some data. So maybe we have a cloud API access to these models. So we supply some data, maybe image, and we get back predictions, such as classification, whether the image was a cat or a dog, or could be anything. Or if supposing this model was some financial model which decides whether I should be given a home loan or not, then I supply my sort of financial data, and the prediction is yes or a no, right? So we'll actually spend a bit of time on this slide. So when this process happens today, I, as a model consumer, I have little visibility to what's happening on the left side of the picture. So all I know is when I supply some data, I get yes or a no. I have no visibility how that yes or a no was arrived at. So these days, a lot of decisions are taken by sort of at least AI assisted or AI made using AI models, such as your credit risk or whether your loan should be processed or not. Now, since I don't have visibility, I'm not sure about certain things like so Bob and Alice cannot find out whether the same model or the same criteria was applied to process their loan applications, right? So this is the problem that we are trying to address. Like, we are trying to add more trust or verifiability to this AI pipeline, where we can, the end consumer can verify such consistency, like the same model has been used, like it's not discriminating against me, or a certifier, for example, some certifier can even check whether the model is fair, let's say in processing loans of male applicants or female applicants or stuff like that. So how do we do that, right? One way is, like, if all these data sets and models are out in the open, then we can verify simply by running the predictions against them. But that is a problem for the respective asset owners, right? So data owners don't want to sort of leak their confidential data. Similarly, model owners, the model represents intellectual property for them, so they don't want to put out their models in the open. So I mean, it would seem that we are arriving at a paradox, right? We want greater visibility. We want to know how these predictions are obtained. At the same time, we don't want to show these assets to anybody. So this is where the cryptography comes in, right? So what, and in particular, the technique of zero knowledge proofs comes in. So what we demand that these asset owners, so whether they're data owners, data curators, or model owners, they publicly publish a hash of their assets. So let's say they publish hash of the data, and similarly, data curators, when they create these curated data sets by applying certain operations on this on the data that they have gathered, they publish the hash of the curated data sets. Similarly, model owners also publish the hash of their models. And let's say they publish at some place which is trusted. So it could be maybe a blockchain, right? A decentralized ledger of blockchain. So some trusted place, they publish hash of their respective assets. Now, does that solve the problem? And by itself, it doesn't, because using these hashes, we cannot verify anything. Like, we don't know whether this prediction came from this data just based on the hash of the model. We need the actual model. But thanks to zero knowledge proofs, now we can actually make this claim only using the hash of the model or hash. So we can make a claim like this prediction came from running this model on this data just based on the hashes of the model and data respectively. And this is what we'll go in the later part, right? We'll illustrate a bit how. So is the problem setting clear? That somehow we want to verify the claimed relationships on data and models just using their hashes.
One question, not
yes.
exactly related to the zero knowledge proof, but in this pipeline, is it only one directional, or do the model owners, for example, go to curators to include some more features, or some either longitudinal or
yes. I mean, so this is a very simplified picture at the moment. This is more a plausible. So model owners, of course, would maybe go back and forth with data curators, asking them maybe to curate data in a better way, or include more features, or include data from more owners. Or that can happen, but when they have settled on, let's say model owners and data curators have settled on that this is the model I want to benchmark, this is the curated data set I want to benchmark my model against, at that time, the model owners can ask data curators to publish hashes of those data sets, right? So once they've agreed on it, they can publish the hashes and also publish how these data sets were curated, right? Like including maybe data from these owners and all. And eventually we'll want all these relationships to be verifiable just using these hashes. Yes, so the back and forth can happen, and once you finalize on the thing, at that stage you can publish the hash. Yeah, the end consumer is not normally interested in that it should be able to verify what you're claiming. Yeah. So let's just consider one example of this pipeline. Or maybe just a bit more time. So one more. So sometimes this pipeline may not even involve these many steps, right? It could be extremely simplistic. So one thing could be there is a private model, and then there is some data supplied to it, and you get predictions. And there is an auditor who just wants to know that a particular model was used on this data to supply this particular prediction, right? So that you're faithfully using a model. So, and this auditor can just make this audit without even seeing the model, or in some, you can even hide the data. The data itself could be sensitive, personal data of people, right? So the auditor can do this auditing without looking at the model or the data, and it can simply audit that yes, the predictions were derived in the correct way, right? So a lot of these things even make sense for sort of this privacy preserving audit and stuff. Okay, so one example of this pipeline that we can see is testing. So these days in AI, you want to test models for like fairness or they're bias free or fairness. So one thing could be like if it's a model processing loan applications, does it discriminate based on gender? You might want to know whether so the model owner is trying to show that its model is fair, and the model certifier is essentially trying to verify if the fairness claims are genuine, right? Like the model doesn't discriminate between male and female applicants, right? So how can so using this pipeline, this claims of fairness can be tested just using the hashes of the respective assets involved, right? So the data owners whose data is being used to, so let's say there's benchmark, there will be some benchmark data sets set on which this fairness is to be shown. So this benchmark data set is created using, let's say, some reputed data sets on loan applications, right? Maybe from major banks which process loans. And then it's shown that model achieves some fairness metric like predictive parity on both male and female applicants. Now, to fully verify this, one, you want to make sure that the model does achieve, so the claim, so the model which has been hashed, it does achieve predictive parity on male and female applications. Secondly, you also want to know that this data that was used to show the fairness, namely the set of male and female applications, it was not some randomly cooked up data, right? That it was actually obtained from these data that is published by these reputed organizations. And so we can also verify the relationship in the first half of the slide, right, on the left side, that these data sets are actually obtained from the data sets published by these reputed organizations. So in that way, you sort of get an end-to-end provenance of this model, right? That it does achieve fairness on the benchmark data set, and that the benchmark data set was properly obtained. So just to revise the setting once more, so there are data owners who want to monetize their data by lending high quality data to specialized organizations. Then there are data curators. They procure data and curate data for specialized tasks, and they want to claim that data was curated from reputed sources. Then there are model owners who wish to monetize their model, and they want to show competence of their models on curated data sets, right? And finally, there are model consumers, and they want to establish, as we discussed, provenance of the results, the models which were used to obtain those, and want to ensure consistency and fairness, right? Consistency is like the same model was used to process Alice's application as the one that was used to process Bob's application. And fairness is that it doesn't discriminate based on sensitive features like gender or etc., right? So now we'll just give an overview of some of the cryptographic tools that help us achieve these aims, right? So, and one of the really simple tools is hashing, right? So what hashing allows is, hashing allows an asset owner to publicly commit to their private asset. So the actual data and model is private, right? But we still need them to sort of make some public signature or a fingerprint, publicly commit to some fingerprint of their asset, right? So it's that function is served by a hash. And why it's needed is because even though the hash does not allow one to infer what the data of the model is, it actually binds the asset owner to this data or model. Like they cannot later adaptively change their model, right? So for example, because if I'm not showing my model and I want to prove that my model is fair, and I receive a benchmark data set on which my performance is actually not good, I can actually change. I can use a different model, right? I can switch the model at that time adaptively, because after seeing the benchmark data set, I decided, okay, my model is not good enough on this data set. But what this hash allows to do that, now you have made a commitment to this model, and now you have to use this model only, because we will ensure that the hash, we can verify that the model that you're using to derive the fairness metric or accuracy matches to this hash. And the assumption is you cannot find two different models that hash to the same thing. So yes, so hash is important in some sense to make a public commitment to otherwise private asset, which we were doing in the previous slides also. And finally, the sort of the centerpiece of this talk, right? The zero knowledge proof. So what does zero knowledge proof allow is it allows us to prove claims over private assets using only their public commitments. So consider the picture on the left. So there is a model. When you input some data to this model, so the data in blue is, let's say, the samples, right, in which on which you are trying to get predictions, and this model's outputs the predictions. So that is happening in the so those are private assets, and if you had access to these private assets, you could have actually verified it by just running the prediction function. But so those private assets are only available with the person who owns these assets, right? To the outside world, we only have these hashes of fingerprints of these assets. So we have some hash of the model, some hash of the data, and some hash of the predictions. Now the question is, can I make the same? Can I verify the same claim? Like this prediction for corresponding to this hash was obtained by running the model corresponding to this hash on data corresponding to the blue hash, right? And zero knowledge proof will precisely enable us to do this thing, right? To solve this problem. So now we can simply verify this relationship over these hashes. So I'll start with an example of a simple zero knowledge proof, just to give an idea about this whole notion of zero knowledge, and then we'll sort of try to get to how you actually, do something like a more complicated relation we discussed here, right? Like that the prediction is obtained from the data. So we will not be able to furnish all the details, of course, within the scope of this talk, but I will still try to give some idea. But before that, I'd like to sort of briefly introduce this notion of zero knowledge, because it is a very elegant notion in some sense. And for that, we take as an example, we take what is famously called the discrete log problem. So for that, we consider this set. I've taken an example set where you have numbers modulo 23, right? So 23 is a prime, and it's important that the number be prime. So we have this set of numbers 1 to 22, and we define a multiplication operation on this set, which is a normal multiplication, except that we keep reducing the result modulo 22 or modulo 23. And we consider a specific subset of this set, which is essentially obtained by taking all the powers of 4, for example. So we have 1, 4, and then 4 square, which is 16. Now, when we do 4 cube, which is 16 into 4, we get 64, which if we reduce it modulo 23, we get back 18. Similarly, 18 into 4 is 72, which again, reduce modulo 23 is just 3. We keep doing this, we'll get this set of 11 numbers. and then we cycle back to 1. So once we get to 6, if we do 6 into 4, that is 24, which is just 1 mod 23. So you get back 1. So essentially this set is 1, 4, 4 squares, all powers of 4. So this we call a group. So this is an example of a group. So and this group has 11 elements. So in general, a prime order group of p elements generated by a generator G consists of elements of the form 1g, g square, all the way till g to the power p minus 1, right? So in this case, our p is 11, which is a prime, and our g is sort of 4. Now, the interesting part is if we are given y, which is y, which is g to power x, we call x to be the discrete log of y with respect to g. So this is just like we normally define log, right? Except that we are working over discrete numbers, so we call it the discrete log. So x is called the log of y with respect to base g. And the issue is for large values of p. So for illustration, I just chose a very small prime, p, which is 11. Finding this discrete log is considered computationally hard. So for example, in this case, 4 to the power 5 is actually 12. But if I just give you 12 and ask you what power of 4 is 12, you can't, there's no algorithm to sort of compute 5 and say 4 to the power 5 will give 12 in this group, right? Because you literally basically have to try all the possibilities. And when this p is really large, let's say some 500 digit number, so p is 500 digit prime, you basically cannot find it unless you try that many possibilities. So the discrete log is hard because, as you see, numbers sort of, because of that modulo reduction, it sort of increases and it decreases, and there is no really set pattern, right? Okay. But so as you said, computing the discrete log is hard. But what if I know the discrete log and I just want to convince you that I know the discrete log? So let's say there is such a group as we discussed on the last page, and p is so I know some x and g to power x, I compute g to power x. Or let's say there's a p and I know an x such that g to power x is p. So linking back to the previous slide, we can think g is 4. So g is known, and p could be something like 12, right? In which case x would be 5. And the problem, so I want to convince this verifier that I know such an x. Now, this problem is interesting only when it is hard to compute such x, right? So for example, if I take some easy problem, like I know the GCD of 2 numbers, that's not an interesting problem because everyone knows GCD of 2 numbers, because there's a high school algorithm that will enable anybody to compute GCD of 2 numbers. So the problem is interesting only when the relation sort of, it's hard for anybody to simply compute such an x. Okay, so let's say a prover has an x. So we call this the prover because he's trying to prove that he knows an x for this p. And the verifier, he only knows g and p. She only knows in this picture g and p, and prover is trying to convince that it knows the x. So one simple way is prover can simply send the x to the verifier, and then verifier can compute g to power x, and she can compare if it's p. But that is like prover is leaking its secret information, right? Why? Because it may not want to leak, because let's say you have an access to some premium parking slot. If you can show that you know such an x. Now, if I tell this x to other people, they can also make use of that x and then have access to my premium parking lot. So I just want to show that I know such an x, but I don't want to reveal this X. So what the prover does in this case is it chooses a random R, and it sends A, which is G to power that random R. Then what the verifier does is it sends back random C to the prover, and essentially it asks the prover to send a Z such that G to power Z so is A into P to power C. So let's just see that this would work. So prover sends initially gets R, it sends G to power R, then verifier sends C, and then the prover actually sends Z, which is C times X plus R. So if the prover correctly sends the Z, we can see that that equation would hold. Like G to power Z would be G to power C into X plus R. Now we know that G to power X is supposed to be P, so that becomes P to power C, and G to power R is what the prover sent. Initially, that is A. So that should equal to A into P to power C. So on the next slide, let's dissect this. So why do we call that this is a zero knowledge proof that the prover actually knows X, right? So let's dissect this a bit more. First, let's see if how useful is this. Okay, let's first see why the prover can correctly send the Z only if it knows an X. So what the verifier actually is doing is the prover doesn't want to send tell the log of P, right? Log of P is X. That the prover doesn't want to tell. So initially, what the verifier allows the prover to send some random element whose log it knows. So it allows the prover to send A, where prover knows the log of A because which is R. And now verifier just cooks up a problem which you can solve only if you could have solved the original problem. What was the original problem? That the prover can solve log of P. And so verifier says, okay, tell me the log of A into P to power C for a random C. Now we know that log of A into P to power C is essentially C times log of P plus log of A. A prover was anyway allowed to send A such that it knows log of A. And so it can compute this log of A to P to power C basically by doing log of A plus C times log of P. So essentially to compute this, it must know log of P because the C is random. So if the prover can answer this random question correctly, so the verifier concludes that because C was sent at random, it actually must know log of P. So this is for verifier to sort of get convinced that prover actually knows log of P, right? But let's see from verifier's point of view, does verifier get any additional knowledge? Does it so what verifier sees here is A, C, and Z, right? The three messages. A was sent by prover, then C was generated by the verifier, and then finally the prover sends Z. So this is what the verifier sees as part of this proof. But the question is this any useful to the verifier? Like, for example, does it tell the verifier anything about the secret X? And the answer is no, because this ACZ is sort of a randomly distributed set of three numbers. It's randomly distributed subject to the constraint that G to power Z is A into P to power C. So because the prover randomly picked R and verifier then randomly picked C, and the Z, and final Z was essentially satisfying this, was sent so that it satisfies the equation G to power Z is A into P to power C. And the verifier, if this is imagine this in some way, this ACZ is useful to this verifier. It allows him to do something useful. The whole point is it doesn't need the prover to get this ACZ. It can sample from the same distribution on its own. So what the verifier does, it randomly chooses a C and it randomly chooses the Z, and then essentially chooses A to A in a manner that so that that equation is satisfied, right? So it chooses A in a manner such that G to so A it chooses C randomly, Z randomly, and sets A to be equal to G to power Z into P to power C. And in this way, it gets A, C, and Z distributed exactly as they were when they were coming from the prover. So if this was any good, if this interaction was in any way good to the verifier, it allowed him to do something, well, he doesn't need the prover for it. He could have generated these numbers distributed like this all on its own, right? So thus the proof in some sense comes from the same random beacon which verifier can itself simulate. And this is the reason we call this proof zero knowledge, because the messages that you see in such a proof are messages you could have generated yourself. Now, so when the prover, the only difference is that the verifier is choosing A in the end, right? The prover was sending A in the beginning, and then verifier sent C, and the prover was only able to send the last message Z only if it knew the solution to that problem, that it knew what that X was. But this restriction does not apply to the verifier because it need not go in that sequence. It can first pick C, then pick Z, and then just set A accordingly. So any questions on this? We can go over this maybe once more.
So just one question.
Yes, yeah.
Here, the modulo operation, does it? So for example, you have A equal to G to the Z, P to the minus C. So with modulo operation, will that still hold? Is there any issue with that?
Yes. So the way we interpret modulo operation minus C is that we take inverse of P, and then we take that to the power of C. So it's P inverse. So with these groups, you always have inverses of elements. So like if you have 4 and like 4 and 6 are inverses. So if you do 4 into 6, you'll get 24, which is 1, right? So in some sense, 6 is 4 inverse. So similarly for 16, you will have 13 as the inverse. So so this group is closed with respect to inverse. So what we so essentially, which means it's closed under all such operations like taking P to power minus C. So when you do minus C, it's essentially saying you do P to power minus 1 and then raise it to the power C. Yeah, and P to power minus 1 exists for all P. Yeah. So yes.
And this equality is also in the sense of modulo.
Yes. So all this is in the sense of modulo. So our set itself is. So I have given the modulo, this set modulo, because normally this is sort of easy to describe this set, but in general, in math, what they call it's a generic cyclic group of ordered P. So typically they will be like based on elliptic curve or something. But just to illustrate, I've just chosen a simple modulo group with this modulo operation, right? But in general, it can be anything that that has this multiplication operation. It could be matrices also. It could be anything that has a notion of multiplication. Yes. So yeah, but the key point here is that the messages that you see in the proof are essentially are random looking messages, and those random looking messages you could have generated on your own, with exactly the same distribution. So if the original message was any good, so note that when we are saying the zero knowledge, we are not even trying to say how we measure knowledge or what is useful to you, what is not useful to you. All that we are simply not bothered. We are saying if in any case, in any way where the original interaction with the prover was useful to you, you can simply replace it by a simulation of your own, right, without needing the prover, and feed it to the same algorithm which yields something useful. So it's totally independent of what you consider useful, useless, and it's essentially saying that the data you get from the proof is you can generate that data yourself. So, so the zero knowledge proof which we just saw. So there are three properties, in fact, that it has, and that is what make it useful. So first is the completeness. So in the previous case, if a prover knows the correct X, it will always succeed in the protocol. So if it knows the correct X, it will always be able to supply this last message Z. So whatever challenge the verifier, whatever C the verifier sends in the second message, prover will always be able to reply the correct Z in the third message if it knows X. If it doesn't know X, then that's a problem. It can't. And so that's the completeness property, that the correct prover will always succeed. Now there's the soundness property, which is sort of the reverse of the completeness. Whereas if the prover does not know the correct X, it will only succeed with very small probability. As in, like it, and the reason is that if it does not know the correct X, this a into p to power c, because c was picked randomly. So after having seen a and p, the verifier knows, and it has picked c randomly. So a into p to power c is a completely random element now. And essentially what the verifier is asking prover is to send z, which is the discrete log of this a into p to power c, which is a completely random element. And we assume that, you know, that finding the discrete log is sort of hard in this. So it's like the prover should be able to sort of solve a random discrete log to be able to reply the correct z, which, as we said, we assume that that's not possible, right? That the problem is computationally hard. So only if the prover knows the correct X can it reliably answer this correct Z. So this is completeness and soundness. And thirdly, the most the important property that we had, that verifier learns no extra information from the proof. So it just learns that prover must know such an X, but it does not learn anything more. In particular, it also does not get any idea about what that X is that the prover knows. Okay, so this was this example showed zero knowledge proof for a very specific relation which is defined by this discrete log property, right? So essentially, this is a proof for relation x comma p, which is defined by p equal to g to power x. But we did not restrict ourselves to these special relations. This was more for illustration. We can also consider general relations over secret values. So remember, we are interested in relations like there is a secret model which has this hash. There's secret data which has this hash. And we want to know that the prediction is actually a result of applying this model to this data, right? So, which is a much more complicated relation than the discrete log relation here. But these are the building blocks. So from here we go step by step, and we end up with sort of relation of any complexity we can prove in zero knowledge. So next, we just see which are the kind of relations relevant for AI pipelines, and then we'll also see how the relations are specified. If you want to generate a zero knowledge proof for a relation, you have to sort of describe a relation in a certain format. It's almost like if you want to compute something on a computer, you have to specify that computation in a specific format using the construct of a particular programming language, right? So similar things hold here, like you have to describe that computation in a specific format. Okay, so one relation, let's just revisit how do we frame the verifiability from a private model, right? Verifying inference from a private model in terms of like verifying a mathematical relation over some unknown quantities, right? So discrete log was an example of it, where X was the secret So I'm denoting this X in red color because like this data is supposed to be secret. And P is again denoting the data which is public, just like a discrete log thing where P was public and X was secret. But now the X and P, now they are denoting much sort of more complicated things. So you can all think of them as vectors containing several data elements. So the relation that we are interested, which will prove that, so the relation which will establish the correct inference, right? So that the red model, when run on blue data, gives this green data. When you want to run over hashes, the way we formulate it as a relation is that we let X, which is D, comma M, comma I, which is the sort of the data model and inference as the private data. And we have P, which is HD, HM, and HI. So which are the hashes of the data model and inference respectively. This is the public data. This is what verifier knows. And what the relation governing them should be that I is essentially predict of M, comma D. So like run the prediction algorithm using model M as the input and data D. And HD is supposed to be hash of D. HM is should be hash of M, and HI is supposed to be hash of I. So this would be the relation that if we can prove in zero knowledge. So assuming we can prove this relation, we have a zero knowledge proof that proves this relation. We essentially can be sure that so essentially we can verify this property over hashes, right? Because the proof will say that the secret D, M, and I satisfy all those properties, that the hashes correspond to those D, M, I, and further that I is predict of M, comma D.
So, sorry, just one question related to the previous example. Can I ask one question?
Here?
Yeah. Okay. Yeah. So here G is common knowledge, right?
G is common knowledge. Yes.
Okay. And the what the verifier is doing is checking whether G to the Z equals A multiplied by P to the C.
Yes.
Okay. And A, P, and C are all known to the verifier, and Z was received just now.
Yes. Z was supplied by the prover as third message. Yes.
Okay. And even though Z is known and C is known, the verifier can't figure out X because a verifier doesn't know R. That's the point.
Yes.
Achha.
That is precisely the point. So R was in some sense sent as a blinding message that blinds the this X, right? That blinds the relationship between Z and R, essentially, Z and X.
Yeah. Okay. All right. Thank you.
Yeah, that is the informal intuition, but when you formally argue, but actually, the more accurate way is to say what I just said. Whether you can figure out X from this Z, I mean, maybe you can figure out at least some partial information about X. Is in the sense if you look at ACZ as the transcript of this proof, you can generate this transcript with same probability. So assuming there is some magical algorithm that if you feed this interaction, it figures out, it outputs something useful with some probability, you can just generate this transcript on your own, which has exactly the same distribution. So that magical algorithm will spit out something useful with exactly the same probability. So that is in some sense the intent. That this, So in fact, even if the problem is easy, right? Even if technically zero knowledge proof doesn't mean that it should be hard to figure out. It just says that the proof doesn't add to your ability to figure out. So whatever you could have figured out about X from this Z, well, you could have figured out without using this proof also. So that's what the intent is. Yeah, it doesn't add to your capability, but you may originally have capability, some capability. Yeah.
Yeah. Okay. Good. Yeah, this is a good point. So it's not saying anything about whether how hard it is or how easy,
Yes.
but just saying that there's no additional knowledge
Yes.
that you can.
So let's say take a quadratic equation, right? You can give a zero knowledge proof for showing that you know a root for this quadratic equation. Of course, you can compute the root yourself, right? But that proof will not add to your ability to compute the proof. Yeah. So you can give zero knowledge proof for completely trivial relation. In fact, any proof is zero knowledge in the sense because you already can solve that problem. So in any case, it cannot add anything, right? Yeah.
Okay. All right. Thank you.
So, okay, so now let's come to maybe a lot of people are from electrical engineering background, so they might appreciate this. How do we actually how do we express these relationships that we want to verify using zero knowledge proofs? And the answer is we have to specify them using what we call arithmetic circuits. So they are very similar to the Boolean circuits, which we all have, only that the gates here are a bit different. So, so just like a Boolean circuit, an arithmetic circuit consists of input wires, some internal wires, which is like the interconnection of gates, and you have some output wires. And then we have gates, what I call arithmetic gates. Now, in Boolean circuits, we have Boolean gates like, I think, and or and, right? In arithmetic circuit, we have addition and multiplication gates, and they do exactly what they sound like they do. An addition gate will add the, so the output wire will essentially be addition of the input wires, except this addition is again a modular addition. So we choose some large prime P, and all of this is done modulo P. Why this is, the advantage is if the prime is really large, a modular addition sort of behaves exactly like a regular integer addition. And same for multiplication, because if your numbers are small, you will never overflow that range. So but yeah, so the circuit consists of addition gates and multiplication gates, and then you have wires connecting these gates, right? And now you say that this arithmetic circuit represents a relation R over some tuples x comma p if it can be satisfied with x as the input wire. So you set whatever is your data x as the input wires, and you set your data p as the output wires, you should be able to satisfy the circuit, as in you should be able to provide values on the intermediate wires such that all the gates in the circuit are satisfied, right? Then we say that, and you should be able to do that precisely when x comma p belongs to your relation of interest. So let's think of a model example, like model and data and inference. So assume x1 is the model, x2 is the data. So right now this is a single point, but you sort of imagine it as collection of wires, right? There are many wires. So for data, you need a lot of wires, right? And for model, so, and x3 is your prediction, right? And then, okay, we should have had a p3 also. So let's say p1, p2, p3 can be the hashes of these x1, x2, and x3. So now you say that, you know, the inference, so you have to design the circuit in a way that it can be satisfied only if the data x3 is the result of applying model x1 on data x2, right? So in general, this is the way we have to describe a computation to be able to verify it in zero knowledge. So we'll look at some examples of how we can enforce these constraints. So another way to say capture this arithmetic circuit is we can describe it in terms of degree 2 equations. So arithmetic circuit can be equivalent to describe where equations of degree 2 over the wires, right? So when you have an addition gate A, B, and C, you can essentially capture it as an equation of the form C equal to A plus B. Similarly, when you have a multiplication gate with A, B, and C as the wires, you essentially, what you're saying is it's described by the equation that C is equal to A into B. So your complete circuit essentially translates into a set of equations which are either linear like additive type of equations or multiplicative type of equations. And whether the circuit can be satisfied is same as whether all these equations can be simultaneously satisfied. The third I've just included, very often you want to force certain values to, let's say, have binary values, and the way you can enforce that in an arithmetic circuit is that you put a multiplication gate there where the wire is A is both the inputs also and outputs. So essentially A square is equal to A, which essentially means the circuit will only be satisfied when that particular wire A has values 0 or 1. So this is normally the tricky bit in designing zero knowledge circuits, like how do you capture a relation of interest as these gate constraints, right? So now let me just give the outline of how zero knowledge verification of operations on data sets works, right? So first, of course, we have to map data sets to input wires of the arithmetic circuit. So just like circuits we design on breadboards, or like you have to map your input data to some ports or some wires. So same is the case here. You have to map data sets to input wires of the arithmetic circuit. Map the public hashes, so which is sort of the public information that you map to the output wires of the arithmetic circuit. And finally, you introduce gates to enforce the constraints, right? So you want to make sure that this circuit is satisfiable only if the data sets which are fed to the input, which are mapped to the input wires, are related via the operation of interest. So let's say operation can be concatenation operation. Like data set C is the result of row-wise concatenation of data set A and B. So if you are modeling this relation, you want to make sure that gates in the circuit are such that they will be satisfiable only if the data sets are indeed related via concatenation relation. So once we have designed the circuit, we just use a sort of a general zero knowledge proof framework to show that circuit is satisfiable. So there are, in fact, now there are general tools available. Once you give them circuit description and you give the assignment of the input wires, they will generate the zero knowledge proof. Okay, so what is the key design constraint? When we are designing these constraints, the goal is to minimize the number of gates in the circuit. So you want to keep the number of gates to capture a relation to an absolute minimum. So roughly this is the thing. So design in arithmetic, so map your inputs to the input wires, outputs to the output wires, design gates to enforce the constraints, and then use a generic zero knowledge framework to show that this circuit is satisfiable, which means your relation, essentially you can check your relation. And efficiency consideration is that you minimize the number of gates. So I'll just give us a brief intro how now, let's say if we were trying to show something over data sets, how would we go about it? And the first thing that we have to do is somehow map a data set to the input wires of the circuit, right? And what the problem with circuits is that they are rigid. Circuit is a fixed thing. It doesn't, it's not flexible enough to adapt itself to the input. So what I mean is, like, if you have a circuit to sort 8 numbers, it sorts 8 numbers. If your input is 4 numbers, the circuit has no way of knowing that you are only interested in the first 4 numbers or something. You still have to provide all the 8 inputs. Same is the case here. So, but when your data can actually vary in size, you need to put some extra bookkeeping information, which means for each, let's say this data set. So imagine all these entries on the right are some wires in the circuit, right? So we map these, and let's say the circuit is because circuit is rigid, so it will be designed to support some maximum size of data. So let's say in this case, 8 is the maximum size. So we map these the actual data to the wires of the circuit. We will always have 8 wires, but the data can be smaller. So what we do that if data is smaller, we'll simply pad the remaining things with zeros, but we also need to store that information, how much is the real data. So for that, we also introduce extra wires to essentially capture the size information. So essentially to then represent any data set like this, we need extra wires like which keep the size information and the padding. So this shows how a data set will be sort of represented in circuit. Okay, so once we have represented it, as we said, we also want to hash the data set, right? So sorry, I'm now getting slight into technical details, and probably not all of this will make sense, but just wanted to give a brief overview just to complete the story, how it goes. So essentially the idea is to hash this data set, and what we do is we hash each column individually. So not go much into this hash, assume that the hash of each of the columns is essentially hash of the private data. But now, how do we verify, let's say, some operations over data sets? Now, remember that data sets are encoded because circuits are rigid. So even so data has to be encoded sort of into that fixed rigid format. So we have, let's say, data set of size 4, and we concatenate it with data set of size 2. So they have all this bookkeeping information that 4 is the size, 2 is the size, and we should end up with the data set of size 6. So in the encoded format, this is the correct operation, concatenation operation, right? So when we perform operations, we must also suitably adjust the size of the padding and the bookkeeping information, right, to maintain the consistent encoding. Similarly, if you perform selection based, let's say, on you're picking up a subset of rows from the source data set, again, you have to ensure that the extra bookkeeping information is also correctly manipulated. Now, how do we verify this? If all these were wires in a circuit, the question is, how do we verify, let's say, a selection operation? Can think of probably even how do we verify it in static electronic circuits, right? And this is hard because, as we said, we have to capture this relationship. So let's say we are trying to capture, verify this relationship that given a vector f and some source data set ABC, the resulting data set is XYZ. We said that we have to express our equations in form of addition and multiplication, but it's not immediately clear how do you express this filtering as addition and multiplication. So, but so we need some tricks of the trade for that. So we will to help the proof, what we say, we will have an auxiliary vector sigma, which is like just once where the target data set for the legitimate rows of the target data set, right? And now essentially what you say is the selection is proper if there is a permutation, if there is the shuffle you can do on F to get sigma, and the same shuffle should take ABC to XYZ. So what you can say is that this is a proper, filter operation is correctly performed if the rearrangement that takes F to sigma, the same rearrangement takes ABC to XYZ. So that you can see here. So this is a rearrangement, sort of a permutation that takes F to sigma, and if you apply that same rearrangement on, let's say, A compose F. So A compose F is simply, it masks out the column A wherever F is 0 and just retains the column A wherever F is 1. So you get AOF. And AOF is really simple. So if there's a set of wires representing A and set of wires representing F, AOF is simply multiplication, right? Because F is always 0, 1. So that is simply multiplication. And to verify that the filter is done correctly, you want to say that sigma is a permutation of F, X is a permutation of AOF, Y is a permutation of BOF, and Z is a permutation of COF. And further, you want that all these are same permutations. But we will not show in this talk, we'll not go into how you check that they are the same permutation. But as a last thing, I will just leave you with how we can actually check that two vectors are permutations of each other in a circuit just using multiplication constraints, right? Because permutation does, again, it doesn't look like you can check permutation using addition and multiplication constraints. So this is just a sample circuit which, so there are input wires, let's say U1 to UK, and there are some wires V1 to VK, and we want this circuit to be satisfiable only if V1 to VK is some permutation of U1 to UK. And what the way we do this is we allow the circuit to have a special wire R which can be set with a random value. And then essentially the circuit checks that once you have that random value R, it will try to check that R minus U1 into R minus U2 evaluated till R minus UK. So notice all this is just multiplications and subtraction, which is essentially addition. So just using add and multiply gates, you can compute quantities on the left, and similarly, just using addition and multiplication gates, you can compute quantity on the right, and then you can check them being equal. So it's a slightly tricky how to check two things are equal using addition and multiplication, but it can be done. And this check works because if U1 to UK is a permutation of V1 to VK, then the polynomials X minus U1 to X minus UK and X minus V1 product X minus VK are identical. And since they are identical polynomials, if I evaluate them at a random point R, I should get the same value. That is true. But if they're not identical polynomials, then because if I'm picking R randomly, there's like extremely small probability that this value will turn out to be same, right? Because the polynomial can only have so many roots, and R is being picked from a very large domain. So this circuit, if this relation holds, then of course this circuit will be satisfied. If the relation doesn't hold, as in they're not permutations, then this circuit is satisfied with extremely small probability. So which means somebody can cheat with extremely small probability. So this permutation, as we said, was sort of used here. There were more things, but we will not go into those details as of now. So now we can also do other operations, but before concluding, I just wanted to give some sense of the performance when we try to prove these operations in zero knowledge, right? So we have tabulated here proofs generation time for different operations on data sets with 100,000 rows, right? And containing 32-bit values. We have not mentioned the number of columns because due to certain optimizations that we do, this is largely independent of the number of columns. So proving something like a concatenation relation in zero knowledge takes around 40 seconds. So it's much slower than doing plain text operations. Like if you just can do a plain text concatenation of data sets with 100,000 rows, it will probably just take a millisecond, but here we run into 40 seconds. So as you can see, I mean, most operations here for data sets of size 100,000 are in the order of a minute. If you go to million rows, you will start going into hours. And so this is still, there's a way to go before it can be used, this these techniques can be used for truly large scale data, but even this is an improvement. Even this is a substantial improvement, and you can still probably solve some interesting use cases with this performance. Also, the memory also is prohibitive. So I'm not going to decision tree, but essentially you can represent a decision tree as a similar data. You can represent it as a data set and you can hash it. What I wanted to was just showing how we can prove inference from a private decision tree, right? We just know hash of the decision tree and how we can prove that on. So these timings are like when the data is public and the predictions are public. What we are trying to show is that they come from a decision tree whose only hash is known, right? So this is considering inference performance for decision tree with 1,000 nodes, depth 20 and 50 features. So for, as you can see, data set, if you're only proving inference for 100 samples, that's like under 5 seconds. If you have 1,000 samples, then you sort of get close to 20 seconds. And for 10,000 samples, you are running close to 3 minutes. So again, running plain text decision tree on those sizes is again a fraction of a second. So in general, in zero knowledge, we are like 4 orders of magnitude. We are trailing the plain text computation by 4 orders of magnitude, if you wish. Yeah, so that's all I had. It was, yes, I tried to keep it sort of as much as possible free of a lot of cryptographic details, but at the same time wanted to share a bit of introduction to those techniques. So any questions? Happy to answer if how this might be used or anything, both on technical side and also maybe on application side.
So one quick question.
Yes.
In the last part, you were mentioning that when we are doing zero knowledge computation, we are trailing the performance that would be obtained using plain text by several orders of magnitude,
yes,
right?
Yeah, roughly 4 to 5 orders of magnitude, depending on which kind of computation you're doing. So something which would typically take 1 second to execute would take 10,000 seconds to prove.
Mm.
Yeah.
But what's the computation that is taking much longer? Is it that selection and
no? So okay. So why the computation? No. So actually, so when you have this processing each gate in this circuit is a costly operation in the sense corresponding to each gate, you have to work over extremely large numbers. So as I said, this prime P is really big. It's of the order of 256 bits, right? So it's 256 bit prime, right? It's a big prime, and all these addition and multiplication are happening. It's over happening numbers of this magnitude. So even when you do exponents, when you're raising something to the power of a 200 bit number, even if you do the recursive log algorithm, right, where you compute divide and conquer, right, you half the thing and you compute half power and square it, even then you have to do 200 multiplication, right, because even the log of that number is 200. So you're doing 200 big integer operations just to compute something like g to power x, and so that's why it incurs such a slow round. So on your hardware, this gate is a register, right, which happens extremely fast. But when we are trying to show zero knowledge proof, essentially the prover has to essentially perform some really big integer operation for each of these gates, and so that is part of the problem, that processing each gate is time taking. Second is you need a lot of gates because you're only allowed addition and multiplication, and expressing, let's say, something like a comparison, right? Even expressing something as simple as a comparison between two, let's say 32-bit numbers, you first need to extract the bit representation of it, because so that costs you, right, 32 gates, and then you have to run the comparison algorithm on the bit, so that like costs you 100 or 200 gates just to do one comparison, which would happen very fast on a computer otherwise. So some operation to simulate memory access, array access, so all these. So yeah, so there's trouble on both ends. First, it takes a lot of gates. If you think of this as a assembly language with really minimum instruction set, right? And on top of that, processing every instruction is much costlier. So yeah, you roughly on both ends, you have 100 slowdown, and sort of gives you 4 order of magnitude.
Okay. And one last thing. So here, can any relation be represented by an arithmetic circuit, or there is some?
In theory, yes. So any relation that can be computed in polynomial time.
Okay.
Yes. So in theory, yes, because you can. That's because of Cook's theorem that any polynomial time NP relation, there is a Turing machine, right? So you definitely have a binary circuit, and once you have a binary circuit, you also have an arithmetic circuit, because you can reduce you can force everything to be bits here, as we just discussed, right? By introducing this third gate, you can force everything to be bit, and then you can behave exactly like you are in a binary circuit with.
Okay.
Yeah, in some sense, yeah. So yes, in theory it's possible, but practically it's practically we don't want to go to binary circuits, and yeah, in practically, so once you work with this thing, you inherently have a feeling that this operation can be done fast, and this will really be challenging. Yeah.
Okay.
Floating point is a nightmare. Yeah. Because we only working with integers, then you have to come up with strange ways of expressing floating point arithmetic as in terms of integer arithmetic. Yes.
Okay. Okay. Thank you.
Yeah. Thanks for the question.
I had another question. When you're employing any obfuscation techniques such as differential privacy, does this result?
Okay. No, so actually not applying any obfuscation here, and this actually has nothing to do with differential privacy in that sense. So what we are saying is that we will so let's say so this is telling you that some relation holds, right, over some inputs. Let's say you're learning the prediction from a model, but you're not seeing the model, but you're seeing prediction. Now, if this you are still learning something, you are still learning, let's say, the output of a model on something. So if this still is as differentially private as like so if this information it does leak something. So so what I mean to say, one is I'm not very familiar with differential privacy, but it does not address differential privacy at all. Like if the output, what it says, you don't learn anything beyond the output, but if output allows you to learn something about the underlying secret, that thing is not prevented, right? So if there's a weak differential privacy with regard to, let's say, learning the prediction, that continues to remain there, that vulnerability. Yeah. So there is no obfuscation here, because you are actually trying to exactly prove that certain computation happened exactly, sort of, and this is the output. Yeah.
Are there any other questions? If not, let's thank Dr. Singh for an informative talk. As discussed before, we would like to remind the audience to subscribe to our Google group, which is a mailing list for information on future talks. You can also visit our website for more details. The links have already been pasted in the chat box, and we'll post the recorded video also on the webpage. Thank you and have a good evening.
Thank you. Thanks, everybody. Have a good
Thank
day.
you, everyone.